All right, people at home, here we go. And people here. So we're going to talk about radioactivity. Radioactivity is when the nucleus of an atom begins to fall apart. Now, when the nucleus of atoms begins to fall apart, hang on, kids. When the nucleus of atoms begin to fall apart, they change into other atoms, which is what is crazy, and they give off energy and particles, okay? Now, here's the deal. Some atoms are more likely to fall apart, and some atoms are more likely not to fall apart. If you're a small atom like sodium or fluorine or oxygen or nitrogen, some of the smaller atoms up near the top of the table, your ratio of neutrons to protons needs to be about 1 to 1, okay? If you have about a 1 to 1 ratio, like oxygen is 8 to 8 or 1 to 1, neutrons to protons, if you have a ratio like that, you're going to stay together. If you're a large atom like lead, you need to have about 3 neutrons to every 2 protons, okay? If you get off of this ratio, then you become what we call an unstable isotope of your atom, and you'll very likely fall apart very quickly and turn into another atom, okay? We'll talk more about this later. Now, there are 3 different ways that these atoms can change into each other, and we call them different types of decay, and that's alpha, beta, and gamma. Alpha, beta, gamma, those are Greek letters. Those are the 3 different types of decay. In other words, if you have an atom and it goes through alpha decay, it will turn into another atom. If it undergoes beta decay, it will turn into another atom. Let's talk about mathematically how this works. Alpha radiation. When 2 protons and 2 neutrons are emitted from the nucleus, that's called alpha radiation, okay? Alpha radiation is the largest particle. 2 protons and 2 neutrons, okay? Now I'm going to show you, and people at home, these notes will be posted online. I'm going to show you an example of this alpha radiation. People here are writing their notes, and that's good. But let's talk about alpha radiation. Here's an alpha particle. An alpha particle has 2 protons. I'll just make a P with a plus sign, and 2 neutrons. And they're in one big clump. That's an alpha particle, okay? Alpha particles are big particles for radioactivity. As far as radioactivity is concerned, alpha particles are very large particles, okay? And let's talk about this. How much would this weigh, if we're talking about atomic mass units, how much would this weigh? You have 2 neutrons and 2 protons. How much would it weigh? A proton weighs 1. That's right. And a neutron weighs 1. So the weight of an alpha particle would be 4. And tell me, what would the charge of this be? It's got 2 neutrons and then 2 protons. What would the charge be? It would be positive. Positive what? How many protons do we have? 2. So we would write 4 over 2. We could write a little symbol, a little alpha symbol, plus plus. That's a good way to write an alpha particle. 4 over 2 alpha plus plus with a plus 2 charge. Now this should make sense to you. Remember, going all the way back to the beginning of the year. All the weight of an atom is in the nucleus. The protons and neutrons weigh 1, and then the electrons are on the outside. They have a negative charge, and they weigh 0. Remember that? Okay? So this is an alpha particle. Now, if you're thinking, you're like, Mr. Perkins, something that weighs 4 and has 2 protons, that to me sounds like helium, right? Look up here at helium on the top. You see helium right here? Doesn't helium weigh 4 and doesn't have 2 protons, right? So basically, an alpha particle is really just like the nucleus of a helium atom. So very often, instead of 4 over 2 alpha plus plus, you'll see 4 over 2 He plus plus. Because an alpha particle is just like the nucleus of a helium atom. And guess what? This is where helium comes from. When we when we drill for helium underground, we find these massive pockets of helium, and then we mine them, and then we put them in birthday balloons. That helium came from the alpha decay of elements that are in the Earth's core. That's a true story, okay? All right, so if this is an alpha particle, let's take a look at some massive atom decaying through alpha decay. And I know this is something new, and you've never seen anything like this, but it's also very, very simple. And I mean that very sincerely. Remember we talked about lead being a stable atom, right? Well, let's take a look. Let's make up a lead atom that's not very stable, okay? And let's do some math with it. Normally, lead looks like this. Pb is number 82, and normally it weighs 207, and there is your normal card for lead, right? That's the normal lead that's on the periodic table. Does that make sense? What if we had an atom of lead, and this is a very stable lead atom, by the way. What if we had some lead that had, say, maybe 4 extra neutrons? What if it was, instead of being lead 207, which is this, which is stable, what if we had an atom of lead, or a bunch of atoms of lead, that were maybe too heavy? Maybe it was lead 211. This lead has 4 extra neutrons, okay? So I'm going to write with you, people at home and people here for the first time ever, a mathematical equation showing the alpha decay of lead 211. Ready? If you're at home, I suggest you write this down. For lead, we would write 211 over 82 Pb, right? And we've done this in the past. The weight over the atomic number, then you write the atomic symbol, okay? So 211 over 82 Pb, that could break down into an alpha particle, 4 over 2, and we could write either alpha or helium here, right? I'm going to write helium. Plus, plus. There's an alpha particle. And what other atom? What other atom? All right. The alpha particle that came out of the lead atom, right? How much did it weigh? I'm literally putting my marker here on the number 4, right? So that means the other atom would weigh 207. How many protons were emitted in that alpha particle? 2. So that means this atom would only have 80 protons. We look on the periodic table. We look up there for number 80. Mercury, right? So lead breaking down like this, if lead 211 gave off an alpha particle, it would turn into mercury 207. See how simple that is? 207 plus 4 is 211. 80 plus 2 is 82. The alpha decay of lead 211 would produce helium and mercury 207. Is everybody with me on that? So that's pretty simple. That's pretty simple stuff. This atom has undergone a transmutation. Transmutation. It has turned into another atom. And the last thing I would ask you about this would be this. Do you believe that this new mercury atom that we made, do you think that would be very stable? Somebody give me yes or no. Do you think this mercury would be a very stable version of mercury? You're shaking your heads. No, and that's right. People at home, let's look at mercury. Mercury normally has a weight of 200 or 200.6. But this mercury atom that's been produced from the alpha decay of lead-211, it produced mercury-207. That's pretty far off. This would probably break down again, wouldn't it? All right. So there is an alpha decay. Now check this out. Check this out. Here is a pretty famous alpha decay. I want you to soak this up for a second. The parent nucleus, or the original nucleus, was uranium-235. Does uranium sound familiar to you? Right? The uranium-235, if it gave off an alpha particle, it would end up being thorium-231. This is what happens when we use uranium-235 for nuclear purposes. Does that make sense? All right. Let's try this one real quick. Well, I'll tell you what, we got to skip this one. Let's do the next type of decay. Let's do beta negative decay. All right? The next type of decay is called beta negative. All right. Decay type number 2. Beta negative. There's only going to be 3 real math types. Beta negative decay. In beta negative decay, a neutron in a nucleus decays and turns into a proton. As this happens, an electron is emitted. So if you're around beta negative decay, you will notice electrons being emitted into the air. If you are around an atom that is going through beta negative decay, electrons are emitted. And let's take a look at this mathematically happening one time. Ready? Here we go. Let's say you have 14 over 6C. That's carbon 14. Have you ever heard of carbon 14? It's pretty famous. It's how we date the age of animals that have died. If we can get a bone sample, we can use carbon 14 to date it. Carbon 14, if it breaks down, okay, carbon 14, if it breaks down through beta negative decay, that means, how much do you think an electron weighs? Nothing, right? Don't we consider it is 0.006 neutrons? So the weight change is 0. The charge of an electron is -1. Boom. So you're at 0 over negative 1 e. Or we can write 0 over negative 1 and just write beta. Okay? Same thing. That's an electron. And what else would be left? 14 and 0. What's the weight of this other atom? 14. 6 is equal to negative 1 and what? 7. Boom. Nitrogen. This is how nitrogen is created, through the beta negative decay of carbon-14. Does this math make sense? Negative 1 and 7. So here's what happens. A neutron in this atom decayed and turned into a proton. So you ended up with an extra proton, right? The weight didn't change, because if a neutron changes into a proton, they both weigh 1, right? So the weight doesn't change. So 14 over 6 carbon, if it beta negative decays, turns into 14 over 7 N. That's the beta negative decay. And let's do a beta positive decay of 1 real quick. Last one. So the bell's going to ring, people at home, if you wonder why I'm hurrying up. Beta positive decay. Let me see if I can get an example of a good beta positive. I'm just going to try to look at some of my screen. All right, yeah, that sounds good. Carbon 10. All right, ready? 6 over 4C. That's no, not 6 over 4. Yeah. Carbon weighs 10. I'm stupidly writing this down. 10 over 6. That's carbon 10. That's a very light isotope of carbon. What is beta positive decay? Beta positive decay is the reverse of beta negative decay. Beta positive decay is when a proton turns into a neutron. It's the reverse of beta negative. If a proton turns into a neutron, a positron is emitted. And a positron, I know you're like, what is a positron? It's an antimatter electron. Doesn't that clear it up? That's a joke. But a positron is literally just a positive charge that doesn't have any weight like an electron. Okay? It's not a proton. It's a positron. It doesn't have any weight. And this is an antimatter electron. So don't worry about it any more than that. But here we go. If a proton turns into a neutron, then this is emitted. A positron has a weight of 0, has a charge of +1, and we can write beta. So 0 over 1 beta, and that's beta positive decay. All right? So what would that leave us with? 10 and 0 is still 10. And what and 1 is 6? 5. The beta positive decay of carbon 10 would end up producing boron 10. Does that make sense? And boron normally weighs 11, so this may or may not be stable. You're only off by 1. So those are the 3 mathematical types of decay. The last type of decay that there is doesn't have any math. And that is me just to tell you, anytime any of this decay occurs, gamma rays are emitted. So anytime you have an atom and it is decaying, and through alpha, beta positive, or beta negative decay, anytime an atom is falling apart, its mass is, whether we record it or not, changing very, very subtly, and energy is being given off in the form of gamma rays, which are the most dangerous type of rays there are, way more dangerous than X-rays, okay? So when you're around a lot of atoms that are radioactive, this is dangerous. The gamma rays that are emitted from the nuclei, that will get you, okay? So I know that seemed a little bit rushed. There will be a worksheet, okay? And on the worksheet, I'll also go over these again, doing the little math problems. So no one can, well, I didn't know how to do this. I promise you, you've just got this video to watch, and I'll make you another one, okay?